Now we can take this idea of calculating normal probabilities and apply it to some application problems. In example 3, we have a company that asked employees to respond to the following question on an anonymous survey. I enjoy working for this company, and they responded anywhere from 1 to 5, where 5 represents strongly agree, all the way down to 1 representing strongly disagree. The results were found to be normally distributed. That's some key language that we need to see in order to apply this approach, with an average of 3.75 and a standard deviation of 1.24. We want to find, well, actually let's pause there for a second. So that tells us that we're dealing with a normal distribution with a mean of 3.75 and a standard deviation of 1.24. We want to find the probability that a randomly chosen employee agrees or strongly agrees with this statement. Those two results correspond to an answer of 4 or 5, meaning we want to find the probability that x is greater than or equal to 4. In Desmos then, we'll enter in normal dist, short for distribution, with a mean of 3.75, standard deviation of 1.24. Click the magnifying glass to get our better picture, and then we'll enter in this case, a minimum value of 4. And what we get is a probability of 0.4201. Telling us that company has, if that company selects an employee at random, there's a little over a 42% chance that that employee agrees or strongly agrees with the statement that they enjoy working for this company. In part B, we want to find the probability that a randomly chosen employee strongly disagrees with this statement. That would be the probability that x is less than or equal to 1. So we would change that max to be a 1, and we get a probability of 0.0133. As a quick note here, notice that we didn't set up the statement probability that x equals 1. For the normal distribution, we always have to have inequality statements. So even though there's no answer smaller than 1, we still set up that probability statement as x less than or equal to 1. In example 4, the game show The Price is Right has 2 finalists advance to the showcase, where they bid and then hopefully win that final prize. The values of these final prizes are known to be normally distributed with a mean of $23,000 and a standard deviation of $4,500. So we have that key language about it being normally distributed. Our mean is 23,000, standard deviation is 4,500. In part A, we want to find the probability that a showcase winner will go home with a final prize worth between $30,000 and $35,000. We'll update the mean and standard deviation to match what we have in the problem. And then in this case, we want the probability that x is between 30,000 and 35,000. And that probability is going to be 0.0561. In part B, we want to find the probability that a showcase winner will go home with a final prize worth more than $41,000. That's the probability that x is greater than or equal to 41,000. We'll put that in as our minimum and get rid of the maximum, and we get 0.00003, which naturally would round to 0. But we don't want to enter that as our probability because that would mean that can't happen. So instead what we'll do is say that this probability is less than 0.0001. So it's a very, very small probability, not quite zero, even though natural rounding rules would have us enter 0. In part C, what's the probability that a showcase winner will go home with a final prize worth less than $41,000? So instead of having that be our maximum, our minimum, we'll have that become our maximum, and we get something that would naturally round to 1. But again, in terms of probabilities, that means that outcome is guaranteed to happen. So rather than entering 1, we'll say that probability is more than 0.9999. So not quite 1, but very, very high. So as long as we have a number that rounds to something that isn't 0 or 1, our answer is that value. But if natural rounding rules would have us enter 0 or 1, we'll just modify that to say less than 0.0001 or more than 0.9999.